Hi, I'm David Bonsack, Product Manager for Rheology at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging the windows to your liking. You can resize the video and slide windows independently of one another by clicking and dragging at the bottom right-hand corner of each window. If you get disconnected at any time, please use the instructions you've received to log back in. You can access several different content windows by clicking at the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions. And if you need help, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We'll do our best to answer as many as possible at the end of the webinar. Our guest speaker today is Professor Joao Maia of the Case Western Reserve University Department of Macromolecular Science and Engineering. Professor Maia is the director of the Center of Advanced Polymer Processing and conducts active research in rheology and polymer processing with an emphasis on the development of multi-phase polymeric materials, online censoring of extrusion and compounding, viscoelasticity of multi-phase materials, and extensional rheology. He received his PhD from the University of Wales, Aberystwyth under the supervision of Professor Ken Walters and was previously on the faculty of the University of Minho, Portugal. Joao has published more than 300 scientific works, including 8 patents and more than 80 papers. He was a Fulbright Fellow in 2007, received the annual award of the British Society of Rheology in 2010, and the Morin Lambla Award of the Polymer Processing Society. It's truly a pleasure to have Professor Maia with us today. The title of his talk is Extensional Rheology in Polymer Processing. Joao?
All right, thank you, Dave. Welcome to this webinar on extensional rheology in polymer processing. This webinar focuses on the importance that extensional flows have on polymer processing operations. Why are they so important? Well, the fact is that the rheological behavior of polymers, and most materials for that matter, but polymers in particular, in extensional flows differs dramatically from that in shear flows. And this is due to the nature of the stresses that are generated at the molecular level in the chains. For example, in polymer processing operations, a lot of these are extension dominated, and even the ones that are not extension dominated have a very strong extensional component. So, for example, sequences, polymer transformation processes like blow molding, thermoforming, film blowing, fiber spinning, these are all processes that are essentially extension dominated. And if you want to design the correct process, the right processing conditions for your material, you need to be able to understand what the rheological behavior of that particular polymer in an extensional flow is. Even, as I said, even those that are not extension dominated typically have extensional components to them. For example, flow in mold cavities, when the polymer goes from the runners into the gates, there's a high extensional component to that flow typically as well. Or flow in extrusion heads, for example. So some quick examples here. We have an agricultural film line. This is your typical large-scale film blowing line where the material, in this case it's a low-density polyethylene, is extruded from an annular die and then gets blown angularly, but also stretched longitudinally. This particular line is huge. The bubble has more than 100 feet, or is more than 100 feet high, and the perimeter is actually about 60 feet here. So very big line, but still large deformations involved even in large-scale processes. Another example at a much lower scale now, for example, fiber spinning. In this case, we have multiple strands, dozens of strands eventually coming out of polymer coming out of a die, and these are highly stretched upon exiting the die. The idea here is that the polymer chains are highly oriented in the stretching direction and will become mechanically much more resistant. This is normally quite well accomplished, as you can tell, for example, from the fact that today sports jerseys are almost impossible to tear, something that didn't happen 10, 20, 30 years ago. And the reason for that is because now we understand much better how polymers behave and how we can control this huge stretch at the end when the polymer comes out of the die. And in these cases, this linear stretch can be as high as 100-fold or more. Another example of an everyday process that is essentially extension dominated is blow molding. In this case, it's blow molding of a bottle where we begin by taking a preform, a previously injection molded preform, we reheat it, put it in the mold, and then first that preform is uniaxially stretched, and then it's inflated against the mold walls. So in this case, we actually have two different types of extensional flows being applied in sequence to the material. And another typical example is that of thermoforming, where you have a sheet of polymer that is heated and then is formed against the walls of a mold. And that is also essentially an extensional flow. As I said, that will be the main topic of the webinar today, but even in the characterization or the development of new materials, extensional flow is very, very important. As I said, the stresses are completely different, the stresses that are generated in extensional flows and in shear flows. So for example, if I put my fingers together and rub them, now I have the world's simplest shear viscometer. And this will give me a feel for the viscosity of the material, of the fluid that I'm squeezing here, but I'm not really generating a lot of area. However, if I take the same material, the same fluid, the two fingers, and then stretch them out, now I have the world's simplest extensional viscometer. And what I'm doing is my volume of material is approximately constant, and when I stretch, I have a strand. Now I have a lot of area being generated. So my area to volume ratio is much higher in extensional flows than it is in shear flows. And as a consequence, for example, if I'm developing a polymer blend, when I'm developing a new polymer blend, or I want to understand what's happening, essentially the first thing I want to do is to generate a lot of interface so that then the compatibilizer or the chemical reaction can occur across that interface, and I can have my stable morphology in my polymer blend. And extensional rheology, extensional flows are much more efficient at generating this interface than shear flows, but also they're much more sensitive to the nature of the interface. For example, here in this case, we have an immiscible blend of polyamide 6 with an EPM rubber, immiscible materials, and if I perform a stress relaxation after a step extension experiment, what I see is that the polyamide 6, which is represented by the black triangles, will have a very fast relaxation. If I have a blend now, an immiscible blend of 80% polyamide 6, 20% of EPM, but non-compatibilized blend, an immiscible blend, which is represented there in green, what I see is that the relaxation basically follows that of the polyamide 6. And the reason for that is because the EPM rubber is very viscous, much more viscous than the polyamide, and when we deform the material, that deformation is essentially applied to the polyamide phase. Not much happens to the rubber phase. But now if I add some compatibilizer, if I graft a copolymer, in this case maleic anhydride, onto the EPM, now I'm compatibilizing the two materials. What I see is the appearance of a long relaxation shoulder. a second shoulder. And although it's not that's not the purpose of this webinar, I can tell you that that shoulder basically depends on the strength of the interface. So if we have a very weak interface, we have no deformation of the rubber face. But if we have a strong interface now, and when we apply the deformation, that rubber face is going to be deformed as well, and that is translated into this long shoulder at long times. Or, for example, if I have a TPU copolymer, I can apply extensional flow at relatively low strain rates. Nothing much happens, and the viscosity actually decreases with increasing strain. But above a certain strain rate, and you can see there the strain rate of 10 reciprocal seconds, where that is represented by the stars, at some point we have an inflection of the extensional behavior, and that inflection actually is a consequence of the fact that we are changing the morphology of the TPU. We're going from something that is essentially amorphous and phase separate and with relatively poor phase separation, as you see by the AFM picture on the left, to something that is a semi-crystalline structure, as you can see on the right. So again, not really the subject of this particular webinar, but just shows you the importance of extensional flows and extensional rheometry when dealing with material characterization. All right, so in 2 dimensions, basically we have just one type of extensional flow, which is this, right? As I showed you earlier. Now in 3 dimensions, there are actually 3 fundamentally different types of extensional flows that you can see there represented from left to right. On the left, you have one type of flow in which the material is stretched along one direction, and then because these are typically constant volume deformations, if we stretch in one direction, the material will shrink in the other 2 directions. This type of flow is called uniaxial extension. Okay, examples of typical polymer processes that are essentially uniaxial extensional processes are filament extrusion, fiber spinning, flow through axisymmetric contractions, for example in injection molding, and the Parison stretch in blow molding that I showed you earlier. The second type of flow is what we call biaxial extensional flow, and is represented in the middle figure. Now we're not stretching just in one direction, we're stretching in 2 directions. And obviously, because of the constant volume condition, then the material has to shrink in the 3rd direction. Examples of biaxial extension are the film blowing and blow molding operations that I showed you earlier, as well as the thermoforming, and in general, inflation processes. Anything that involves inflation is typically a biaxial extensional process. Finally, we have a third example, a third type of extensional flow called planar extension. Obviously, we cannot stretch a material in 3 axes. So in this case, what happens is we stretch the material along one axis, the material shrinks in the 2nd axis, and nothing happens in the 3rd axis. Now, what this means is that there must be some sort of constraint along the 3rd axis that prevents the material from contracting or expanding. Because if we leave the material to its own devices, it will go uniaxial, because we're just stretching in one direction. So examples of planar extensional flows are flow through planar contractions, radial flows, calendering, film extrusion, film and sheet extrusion, the flow in prior to the die land in coat hanger dies, for example, where you now have a film of constant width, but you're still getting some contraction in the film before it goes into the die land. So these are the 3 main types of flows, type of extensional flows. Very quickly, just to show you what the flow kinematics looks like for each of these three types of flows. We start off by defining a strain, which is if we have a strand, we define the strain, and we define the strain as the difference in length divided by the initial length. Okay, and now we can calculate the infinitesimal instantaneous strain, so d epsilon, and obviously that will be the infinitesimal change in length, dl, divided by L itself. If we have a stationary flow, we have a constant strain rate, so that means that the time derivative of that infinitesimal instantaneous strain needs to be a constant. So we end up with that expression 1 over L dl dt equals k. Now we can integrate this. We can put everything with L to one side, everything with T to another side, and on the L side, on the left there, we integrate between the original length, L0, and the current length at time t, Lt. And on the right, we integrate between time 0 or T0, the beginning of the deformation, and the current time t. Now on the left, we have 1 over L dl, so the primitive function of that is the natural logarithm. And so after some very simple maths, we find very quickly that the length of that particular filament that we're stretching needs to increase exponentially in time. And that, that rate of exponential increase is our strain rate. Now the velocity is the time derivative of the length. But the derivative of an exponential is still an exponential. So not only the length needs to increase exponentially for one to have a constant strain rate measurement, but the velocity, the separation velocity, also needs to increase exponentially. And that's why, for example, tensile tests on solid polymers are extensional deformations, but they're not constant rate deformations, because the separation velocity between the two clamps is typically linear, and so the strain rate is actually exponentially decreasing. Now, if we take this volume conservation condition and some symmetry conditions from the flows, we can actually define the flow kinematics in those three types of flows. And for example, in uniaxial extension, what happens is that if we define the strain rate as the stretch rate in the direction we're stretching, in the one direction, the material will actually contract at half of that strain rate in directions 2 and 3. So if I'm stretching at 10 reciprocal seconds in the x direction, the material will contract at 5 reciprocal seconds in the y and z directions, as you can see there. The strain rates in directions 2 and 3 are minus 1/2, which means that they are contracting at half the rate. Biaxial extension, now we're stretching. This is the particular case of equibiaxial extension, which is the most common. In this case, we're stretching in both directions, 1 and 2, at the same rate. Obviously, the material will have to shrink in the second direction at twice that strain rate. Okay, and finally, planar extension. The condition is that nothing happens in one of the directions, in this case the 2 direction. So if you're stretching in 1 direction, in the 3 direction, the material needs to contract at the same rate. And so now we know exactly what the flow kinematics in the whole material looks like depending on the type of flow. And to make things even more interesting, now we're all used to dealing with the shear viscosity. And one would think, okay, so now how much is the extensional viscosity? And it's very easy to prove using continuum mechanics that in fact the extensional viscosity in uniaxial extension for a Newtonian fluid is 3 times the shear viscosity. So we can define something called the Troughton ratio, which is the ratio of the two viscosities, and that Troughton ratio is 3. For a biaxial extension, the Troughton ratio is 6. And for a planar extension, it is 4. So now a material, even if it's a completely homogeneous material like a homopolymer, it doesn't have 1 viscosity. It has 4 viscosities depending on the type of flow that one is applying. And things get even more interesting. As most people will know, polymers are what we call shear thinning materials, meaning that in a shear flow, their viscosity will decrease the faster you deform them. And for example, here is the schematic depiction of a typical low-density polyethylene. Actually, this is a standard material that was used as far back as the 80s in a series of round-robin exercises between different labs. And as you can see, we have the typical, for the lower curve, we have the typical behavior in shear flows. At very low shear rates or shear stresses, we have a Newtonian plateau. And as we increase the stress or the rate, that viscosity, the shear viscosity, starts decreasing. Now, if we look at the upper curve, things change dramatically. At low stresses, because all the materials, all the polymers, behave at slow enough flow rates, at long enough times, everything behaves like a Newtonian fluid. So, not surprisingly, at very low stresses, this limit, this Newtonian limit of the Troughton ratio of 3 still holds. The zero shear viscosity of this particular LDPE is about 17,000 pascal second, and the zero extensional uniaxial extensional viscosity is about 50 to 51,000. So essentially 3 times the shear viscosity. The problem is that most polymer processes take place in stress ranges of about between typically 10 to the 4 and 10 to the 6 Pascal. And in those stress ranges, the ratio of the two viscosities is completely different. Depending on the materials, and this is an extreme case of LDPE, this ratio can be in the hundreds. Why? Because in extensional flows, a lot of the materials will be what we call strain hardening. Their viscosity will increase the faster you stretch them. Okay? And as luck would have it, this discrepancy between the shear and the extensional viscosity is highest in the typical processing range of polymer processing or of polymer processes. So really, when one is designing a process, even if one assumes that the extensional viscosity, for example, the uniaxial extensional viscosity is 3 times the shear viscosity, that is not good enough, because that is the Newtonian limit at very low stresses. For stresses typical of your processing, this ratio could be more than 100, and that will alter dramatically your processing conditions and your processing window. So the question is, how do we measure this extensional viscosity? Well, as I'll show you in a minute, there are experimental and physical limitations that make it extremely difficult to achieve steady-state conditions in extensional experiments. And what happens most of the time is that instead of plotting nice little steady-state curves like we have here, we're limited to plotting what we call transient data curves, so transient curves, where we plot the evolution of the extensional viscosity over time for different strain rates. So for example, in this case, and we'll come back to this curve later, each of those colored curves is an experiment at a different strain rate, as you can see there in the legend. Okay? Now, what are these problems? Well, these problems typically have to do with some challenges in extensional rheometry. Okay? It's very difficult to create well-controlled, purely extensional flows in lab conditions. Why? Because it's very simple to say, oh, you take a fluid and you stretch it. But the first question is, how do you grab it? How do you grab a fluid? Right? You know how to grab a solid. Everyone knows how to grab a solid, but how do we grab a fluid? So typically we have boundary conditions that may not be purely extensional. Okay? So we may have shear flows at the boundaries, and I'll show you a couple of examples very soon. Again, the issue of sample clamping and holding. Surface tension. We're now stretching, we're creating a lot of this area, so surface tension plays a role. Depending on how we stretch, if we stretch like this or if we stretch like this, gravitational effects might come into play. Inertial effects if you stretch too fast. So these are experimentally difficult conditions. Okay? Now, in addition to that, there is a more fundamental difficulty here as well, which is the fact that the flow lines in extensional flows are converging in at least one of the directions. So for example, if you're applying a shear flow, if you have flow between parallel plates, as long as your material is stable enough, you can shear, and you can shear for as long as necessary to achieve steady state and get a proper viscosity measurement. Here, because of the converging flow lines, as we stretch the material, eventually we're going to run out of material typically before the steady state can be achieved. And that's why we plot these transient curves. So how do we interpret these transient curves? Well, as I said, we plot the viscosity, the extensional viscosity or the extensional stress as a function of time for different strain rates. Okay? And in blue, you can see there what would happen to a Newtonian fluid. If you start applying a deformation to a Newtonian fluid, it will build up stress gradually, and eventually it will level out. Okay? This is what we call the linear viscoelastic regime envelope. Okay? At very slow deformations, all the materials will essentially follow this curve. And the extensional equivalent of that curve in shear flows, it has exactly the same shape. It's just shifted by that factor of 3 that I told you about earlier. Now, for example, in the case of this low-density polyethylene that we saw earlier, what happens is that because it's a highly it's a highly branched material, the entanglement density is very high. It's a very elastic polymer, and that's why, for example, if we go back to that agricultural film line, that's why we use LDPE, because LDPE, being a very elastic material, can withstand large deformations. So what happens here is that as we increase the strain rate, we get the phenomenon shown there in green. As we increase the strain rate, there's an upward deviation from the linear viscoelastic curve. Okay? And ideally, we would like to have those green curves to level out and have a steady state measurement. In most cases, that is not possible because the sample will rupture before that steady state is achieved. These materials we call strain hardening materials. And the extensional viscosity deviates positively from that limiting factor of 3. In some other materials, for example, and I showed you an example earlier, those TPUs, those thermoplastic polyurethanes, what happens is that there will be a negative deviation from the linear viscoelastic curve, which you see there in red. These materials are called strain softening. That's the extensional equivalent of the shear thinning materials in shear flows. Okay? So typically when one sees the extensional or the characterization, the rheological characterization of fluids in extensional flows, this is the type of flow curve that one sees, not the steady state flow curves. So going back to the challenges that we have, so now we have challenges of two natures. One is an intrinsic problem, which is the fact that we have converging flow lines. The other one is an experimental problem. How do we create the purest extensional flow possible? Okay, uniaxial flow is the type of flow that's been most studied of those three that I told you earlier for two reasons. First, it's very relevant industrially, but secondly, it's also for a very selfish reason. It is the least difficult, I wouldn't say the easier or the easiest, but the least difficult of the three flows to implement under controlled conditions in the lab. And there are two main techniques, general techniques to apply this extensional uniaxial flow. Variable sample length or constant sample length. So we'll just briefly go through both of them because these are very important. So going back to the flow kinematics of uniaxial extension, we know that the length of the filament will increase over time exponentially, as will the velocity. So if we have, for simplicity's sake here, a cylindrical sample, we can apply a velocity at the ends and so forth and so forth. And we know what the velocity field looks like. So for example, in the x direction here, we are stretching at a certain strain rate that I'll show you in the next slide how to calculate. Okay? So because we have a uniaxial extensional flow, we know that if we're stretching in this direction at a certain strain rate, the material will be shrinking in the other two directions, in particular in the radial direction, at half of that strain rate. So Vx the velocity in the x direction, will be the strain rate times the position in the x direction. In the radial direction, you will have a contraction at half of that rate. So varying sample length experiments. Here we have one of the most commonly used designs where you have two plates and you keep separating the two plates continuously in time. Okay? And you should separate these two plates exponentially, right? Because we want constant strain rate, so we know that the two plates need to separate at an exponential rate. Now, we know that the volume is constant, right? And so the volume of a cylinder is the area times the length. So we have the initial area, pi r0 squared L0, and from that we can calculate the area in time, the area evolution in time. And what we find is that the area in time has to also decrease exponentially. So this strain rate can actually be programmed into the velocity profile or via the monitoring of the time evolution of the cross-section, because now if the area decreases exponentially in time, the logarithm, if we plot the logarithm of the area over as a function of time, we will have a straight line, and the slope of that line will be minus epsilon dot. We can calculate the stress. The stress is very simply the force that we measure, because typically these plates have, one of these plates will have a force transducer, so we can measure the force evolution in time divided by the area. So we know what the area is like, and or we know how the area changes over time, and if we divide the force by that area, we have the tensile stress. So if we divide that again by the strain rate, now we have our very own extensional viscosity. Now, for constant sample length experiments, things change slightly. One of the issues here with the varying sample length is that one needs to apply an exponential velocity profile. And that is not always easy. Life would be a lot easier if we could just apply a constant separation speed or a constant. And we do that using, as I said, the constant sample length methodology. Typically what you have there is two sets of rollers. These rollers will be counter-rotating rollers, and the sample sits between the two pairs of rollers. So now the rollers counter-rotate and the sample is stretched out. Now, variable sample length experiments essentially are constant volume experiments. Here we do not have a constant volume experiment because we're losing sample as the rollers stretch it, but this is a constant length experiment. We can define the strain rate very simply by the linear velocity divided by the length of the sample. Now this length now is constant, which is great, and to have a constant strain rate, all we need to do is have a constant linear velocity as well. So we have the angular velocity at each set of rollers. Typically, they're the same. And then you multiply that by the radius of the rollers, of the cylinders, and you have a very simple case of, in order to achieve steady or constant strain rate, all we need to do is apply a constant velocity to these rollers, linear velocity to these rollers, which makes it much more easy to implement experimentally. Again, we know that if we have an extensional flow, a uniaxial extensional flow, the radius will decrease in time at half of the strain rate. And we also know that the radial velocity will be the time derivative of the radius. So the evolution of the radius in time. If we bring these two together, we can calculate very simply that the radius, also in this case, the radius of the sample, assuming it's a cylindrical sample in this case, also must decrease exponentially in time. And that rate of decrease is minus 1/2 of the strain rate. So again, we can monitor the sample, the radius decreasing in time, and calculate the true strain rate. This is important in this type of flow because at the rollers, there is the possibility of slip, there's the possibility of some shear-induced flow there. So in this type of experiments, the true strain rate is normally slightly different from the nominal strain rate. So in this type of in this type of experiments, it's important to calculate the true strain rate. And again, you take the stress, force divided by area, and basically just if you can measure the torque very quickly, you can know the strain rate. With the torque, you can calculate the tensile stress, and again, we can calculate the extensional viscosity. Okay, so just to sum up, both techniques have advantages and disadvantages. Okay, varying sample length, you have to apply an exponential increase of the clamp velocity. Sample holding at the edges is difficult, and it's relatively prone to deformation non-homogeneities. Also, typically, it's limited in maximum strain. The Henke strain is a logarithmic measure of the strain, so a Henke strain of 2.5 does not mean a 2.5 times linear stretch. It means e to the power 2.5 linear stretch. Constant sample length, it's easier to implement, but now, for example, and I'll show you in the next set of slides what's going to happen, it is prone to some experimental errors of which the operator must be aware, acutely aware, in order to get good data. So, for example, let's do a case study of probably the two most widely used extensional accessories today. These are both based on what we call the concept of fiber windup. And one that you can see depicted here is the so-called Saint-Manat Extensional Rheometer, SER, that's typically sold as an accessory to shear rheometers, in which you have the two rollers counter-rotating outwards and the sample is stretched in the middle, as you can see there. And there is also an extensional viscosity fixture that is specific to TA instruments and to the RS rheometer that uses a similar principle of modified fiber windup, although the winding up is achieved by different means. But these are two of the most widely used rheometers. And the advantage that these accessories have is that they're really easy to use. Okay, so what these have done is really open up the possibility of performing extensional experiments to a much wider audience, scientific audience than before. The problem is that they're extremely easy to use. So sometimes it's very easy to fall into some experimental traps, which is what I'm going to talk about next. So for example, it's critical that sample preparation is done correctly. Typically, for this type of instruments, the SER and the EVF, we have not cylindrical samples, but little sheets or little slabs that are typically compression molded. If we have cylindrical samples, they are typically extruded out of a capillary rheometer, for example. Now, in the case of the little strips that are compression molded, one has to make sure, for example, so the residual stresses in those samples are relatively low, but one must be careful not to have entrapped air bubbles. So here, for example, you have the transient extensional viscosity of a polyisobutylene at room temperature, and you see the curve below that levels out. That's the linear viscoelastic curve, as I showed you earlier. The good experiment is the one that follows that linear viscoelastic curve up to about a time of around 3 to 4 seconds, and then starts strain hardening. And then you have one of the other examples, which is the sample with air bubbles inside, or a sample, for example, with surface defects. If any of that happens, you will have a significant deviation from the correct data. And those are the two curves that are completely off the mark there. And that can lead to huge problems when you're trying to model these systems. If you have a sample that's extruded out of a capillary rheometer, then you have to make sure that prior to stretching it, you relax the stresses from the extrusion process in the rheometer. Now, another issue is, and let me move forward actually, and I'll come back to the other one afterwards. Now, one of the problems there is that if you do it, as you put the sample in the rheometer and you prepare it and you bring it up to temperature and you wait for it to relax stresses, which you have to do, you might have sagging. Okay, you might have sagging. So for example, here we have a case of this low-density polyethylene that I showed you earlier, an experiment at different strain rates, and this is a good experiment, please believe me. All right, so we have a nice strain hardening behavior there, no problem. Now what happens if we're not careful and we have sample sagging? Once the sample melts, it will sag a little bit. What happens if we don't correct for that sagging by bringing it up horizontal? This is what happens. Now you have data that's all over the place, and not only it's all over the place, but it's in the wrong places as well. So big problem here, sagging. Sagging in these samples can be a huge issue. Easy to take care of, but the operator needs to be aware of these problems. Okay? How do you avoid sagging? Well, you avoid sagging by going to wide samples. So these strips typically have 1 to 2 millimeters, are typically 1 to 2 millimeters thick, but then we made them wide. But the problem is if we make them wide, and let me go back, now we have this phenomenon. As they become wider, they become less prone to sagging than thin samples. But now this is a graph, for example, that shows the evolution of the sample width as a function of time. And if we have a uniaxial extension, this needs to be a straight line. Okay, this needs to be a straight line with a slope of -1/2 of the strain rate. And you can achieve that for this for the thin sample. Obviously, these instruments have an issue, which is after one full rotation of the rollers, the sample winds on itself. And for example, you can see there that at very high strains, you have deviations from this uniaxial extension, but that's essentially because the sample now started winding on itself. But for the thicker samples, you have a much earlier deviation and a huge deviation from uniaxial extensional flow. So you may think you have uniaxial extensional flow, when in reality you do not. You have a very strong planar component. So somewhere in the middle, there's a sweet spot where your sample does not sag too much, but it's not so wide as to have a significant planar component, the deformation in the deformation. So these are issues that can be addressed, but the operator needs to be aware of. And again, for example, if we try to change the grip to get better grip on the samples, for example, and this is especially in the case of constant sample length experiments, depending on the surface finish of the rollers, of those 4 rollers, you might get better grip or worse grip, and you might end up for the same nominal strain rate, and this case is an extreme case of that polyisobutylene where the nominal strain rate was 0.14. When we used ground rollers, the effective strain rate as measured by the evolution of the radius was 0.062. And if we use toothed rollers, it was 0.034. So differences up to 80% from the nominal value. So again, the operator needs to be careful and needs to be able to understand the data and take the necessary experimental precautions. I said I would go back to this picture. I'm back at this picture. The final result, when you have all sources of error eliminated, or so you think, looks something like this. This is that polyisobutylene I told you earlier, and in this particular material, we were able to perform experiments from down to 2 × 10⁻³ reciprocal seconds, which is the curve in blue. And that experiment, if you look at the x-axis, which is logarithmic, that experiment went on for more than half an hour, about 2,000 seconds. And we were able to go up to strain rates in excess of 6. Which are the crosses there. And those experiments took about 0.3 of a second. So a huge range of times here, huge range of strain rates, but if this is what is possible to do if one is careful with the experimental conditions. So now I will conclude the webinar with a case study of a thermoforming process. Okay, so thermoformed polystyrene. Polystyrene is the material by excellence for thermoforming operations. Very nice, very easy to process, can withstand large deformations. It's transparent, so if you use it for packaging applications, it's great because the consumer can see what's in the package. It has a little problem. It has horrendous mechanical properties, especially the impact resistance. It's very, very poor. And once it cracks, there's a catastrophic crack propagation. So it's horrible. So what happens? How can we solve? How can we correct for that? Well, we normally process that material with a high impact, what's called a high impact polystyrene, which is essentially a polystyrene to which we graft a rubber phase, typically 6 to 10% of a rubber domain, during the polymerization process. What that means is that now this new material has much higher impact resistance because of the rubber phase. It's no longer transparent, so if you have a white, typically if you have a white plastic cup, like a yogurt cup or something, that's high impact polystyrene. If it's transparent, it's what we call general purpose or crystal polystyrene. But normally what we do is we actually process blends of the two materials, because we're trying to get the superior deformation and flowability characteristics of the polystyrene, but also the mechanical properties of the high impact material. So in this case, what we did was we wanted to study the influence of rubber content on the performance of these thermoforming grade blends, okay? In terms of the processability, i.e. how do they flow, the evolution of the operating window, for example, how much can we stretch them and what is the type of rupture that we get and the type of failure that we get in the system. And also we wanted to look at the final thickness distribution. So I'll just show you some limited set of results here. We used a high impact polystyrene, 8 to 9% of this rubber phase, in this case a butadiene, excuse me, which we blended with a general purpose polystyrene. And I'm just going to show you results for the two materials plus a 50-50 blend, although we did test for more. And we start off by doing what we normally do. So we want to look at this problem computationally. We have a part, a computationally thermoformed part, and we want to look and we want to understand what happens. The first thing that we do is we take the three materials, the blend and the two polystyrenes, and we perform shear experiments on them, essentially initially small amplitude oscillatory shear experiments to measure the storage and loss moduli at various temperatures. We apply time temperature superposition so we can have the activation energy of our materials. Basically, the activation energy tells you how sensitive to variations in temperature the viscosity of your material is. Okay? And basically, what we found is that, as expected, as we increase the rubber content in the final material, the viscosity becomes more and more sensitive to variations in temperature. So we have these curves of G prime and G double prime, which I could talk about for like 5 minutes, but are besides the point of this webinar. But basically, they show they show what we expected them to show. And same thing with the shear viscosity. We apply time temperature superposition, and we have 3 shear thinning fluids. The high impact polystyrene is actually, because of the rubber phase, slightly more, is the most viscous. The general purpose polystyrene is the less viscous, and the blend is in the middle. So far so good, nothing unforeseen there. Now, when we look at the extensional viscosity, that's when things start getting interesting. Because here you have the transient viscosity curves for the 3 materials. And again, in blue, we have the general purpose material. In black, you have the high impact material, and the blend is in red. And you can see that at short times, they all follow their respective linear viscoelastic envelopes. All the curves, regardless of the strain rate, fall down on the same linear viscoelastic envelope. But now you can see there, and we can quantify this by the Troughton ratio, but just for illustration purposes, I'm showing you this. The red curves are much more strain hardening than either the blue or the black. you have a much bigger departure, positive departure from this linear viscoelastic envelope. So something is happening, and to be perfectly honest, we're not quite sure what, but something is happening here in the blend that leads to an increased strain hardening of the blend compared to the two initial materials. And we'll see what the consequences are for polymer, for the actual process afterwards. So now one of the things we wanted to do is we wanted to confirm that this blend actually does bring out the best of both worlds. So we know that the general purpose polystyrene is highly stretchable, highly deformable, but has very poor mechanical properties, whereas the high impact polystyrene is not as deformable but has better mechanical properties. So here I'm showing you the Henke strain, so the maximum strain at rupture for different strain rates. And as we can see, we have the blue dots, which represent the rupture points of the general purpose polystyrene, followed very closely by the red diamonds, which are the 50-50 blend. You can see that typically the two curves are parallel to each other, and the maximum Henke strain of the red is about 1 unit lower than that of the blue, which means that the blend is about 3 times less stretchable than the general purpose material. But if you look at the black curves, at the black diamonds now, the high impact polystyrene, much, much lower. Another factor of about 5 to 6. So really what we're accomplishing here is we now have a material, the blend, that still has much higher stretchability, much higher deformability prior to rupture than the high impact material. So the blend from the deformability point of view works. So the question is, how about from the mechanical properties point of view? So we have the Henke strain at rupture. We have the stress at rupture. We can measure that. So we can define a modulus, a Young's modulus at rupture. And again, what we see there is because of the rubber phase now, and don't forget this is in a molten state, the rubber phase in the high impact polystyrene basically means there's a lot of experimental scatter there because these experiments, as I told you before, are difficult to perform. So the experimental scatter is higher than in normal shear experiments. But I would argue that the black diamonds are all basically more or less on the same Young's modulus region, something around 5 to 10,000 Pascal. And because of the rubber phase, essentially the modulus is constant. So the rubber is really responsible for the increase in mechanical properties. 50-50 blend, lower modulus, but still relatively high at about 1,000 Pascal. And again, constant. So the influence of the rubber phase is very clear here. If you look at the blue diamonds, the general purpose polystyrene, very, very poor mechanical properties. Young's modulus of 1 to 10 Pascal. Okay? So what these two results show us is that really by blending the two materials, we do get the best of both worlds. We still get high stretchabilities, even though not as high as the general purpose polystyrene, but we also get those with a good and acceptable level of mechanical properties, which you wouldn't be able to get with the general purpose polystyrene. So now we're happy. We're happy with that. So now let's look at the process itself. So we're modeling the process. What I'm showing you here is the actual modeling of the process, not the experimental results due to obviously time constraints. But we used, some of the audience might be familiar with these more complex nonlinear viscoelastic models, some might not, but we used a model called the simplified KBKZ model. And what this model has, forgetting about the equations for a moment, it has two components. It has a time dependency, which is given by that function m, okay? And it has a strain dependency. This time dependency, the m, is essentially gives us essentially the linear viscoelastic response. So we can get this from the G primes and G double primes, the storage and loss moduli data that I showed you earlier. The strain dependency now is relevant to model the high strains that we have in the process. And we tried two different functions for that strain dependency, and this really depends. The general form is like this, but it can be applied in shear or in extensional flows. So basically, the time dependency will give us the linear viscoelastic behavior. The strain dependency will give us the non-linear behavior. So just to show you the kind of fit that we have, this is for the high impact polystyrene, G prime, G double prime, the symbols are the experimental data, the lines are the results of the fit. So a decent fit. So in principle, we can model quite accurately the linear viscoelastic behavior, the short or the low deformation behavior, or the small deformation behavior. And we can do that with 7 relaxation times. We can actually also do the same thing now with that strain dependency, those what we call those damping functions. And again, we get a good fit to the non-linear viscoelastic behavior. We can pretty much accept at very low shear rates, but we can pretty much capture the shear thinning in shear flows. We can capture the strain hardening, this uptick in the extensional viscosity. So in principle, we're good. We're good to go. So this is the part that we thermoformed. And this part was carefully chosen because there are two fundamentally different types of thermoforming. There's regular thermoforming where you have relatively shallow parts, and the sheet, when the sheet is deformed, it hits the bottom of the mold first and then spreads to the sides, to the side walls. Or you can have what we call deep draw thermoforming, where you have a deep mold and the bubble, as it deforms, hits the walls first and then progresses down the walls until it hits the base. And this particular part has the right side is regular thermoforming, and the left side is actually deep draw thermoforming. So we can take a look at both cases simultaneously. And we did simulations and experiments for 1 and 2 millimeter thickness sheets. So basically what we can do is heat the sheet up to a predetermined temperature, right? And then we follow the inflation process numerically. And I'll show you, I'll direct you first to the graphs to the pictures on the right of the slide, where we have the evolution of the bubble deformation over time for the 3 materials. And what we can see is that for the blend, now because of this higher level of strain hardening, the inflation is actually slower, because the material offers more resistance. This is under constant pressure, so under constant thermoforming pressure. And what happens there is that the higher level of extensional viscosity slows down the process. So, for example, at 9 milliseconds, numerical milliseconds, both the polystyrene and the high-impact polystyrene sheets have finished deforming, but it takes about 25% or a third longer to completely thermoform the blend. Now, if you look at the left, we're just quantifying this difference. So basically, on the left, we have the inflated volume, the total inflated volume, as a function of time. And you have the dashed lines are the results for the 2 millimeter sheets. The full lines are for the 1 millimeter sheets. Okay, and then the light gray are the results for the blend. The thin full line is for the high impact polystyrene, and the thick full line is for the polystyrene. So for example, a thick dashed line means the evolution of the inflated volume of the polystyrene and the 2 millimeter sheet. Okay? And as you can see, it's actually simpler if we look at the results for the 2 millimeter sheet, because obviously the sheet is thicker, the inflation process is slower. So if we look at that, but the same thing happens for the 1 millimeter, we have the high impact polystyrene and the the general purpose polystyrene inflating at almost the same rate. But we have the blend inflating much, much slower. So the total inflated volume increase is much, much slower. So this clearly shows the influence of the extensional viscosity on the flow kinematics of the process. Okay? And we can calculate the thickness distribution profile as well. And we can take cuts across, for example, on the left we have a cut across the deep draw section. On the right we have a cut across the middle where we get both the deep draw and the regular thermoforming sections. And again, we can clearly predict very accurately the thickness distribution in the part. And what that does is opens up the possibility of optimizing the thickness distribution based on the processing conditions. These results, for example, are for a constant sheet temperature of 150 degrees C, but what you could do, for example, is apply a differential or a gradient of temperatures to the sheet and make sure that you minimize, for example, the thickness variations across the bottom of the part. Because as you can see, those results are for the normalized thickness, so the thickness divided by the initial thickness. The thinnest parts in the deep draw section, the thinnest parts are actually at the corners of the base. Now, when you drop something, right, chances are what's going to hit the ground first? The edge of the base. So that is also the most vulnerable part of the the whole cup, or whatever you want to call it. So really, what we want to do, what we might want to do in this case, is tweak the processing conditions in a way that we increase, or at least improve the thickness distribution across the entire base and not make it as thin at the corners. And for that, but again, to model this accurately, we need to have not only the shear flow behavior, but also the extensional flow behavior. All right? In this particular case, because the shear viscosity of the high impact polystyrene is slightly higher, you have actually a more homogeneous distribution along the base. So that leads me to my conclusions. I hope I've made it clear that extensional flows are extremely relevant in most industrial polymer transformation processes, that extensional rheometry can provide crucial information on the flow characteristics of the polymers and on other important processing parameters like the setting of operating windows and maximum stretchability that you can apply on the samples, okay? But that unlike in the case of shear rheometry, even with very good technical training, there are some experimental pitfalls in extensional rheometry experiments of which the operator needs to be acutely aware if we're going to get good data out of this. Thank you very much. That concludes this webinar.
Thank you, Joao. A recorded version of this webinar will be archived and available through the TA Instruments website.